Okay, so now with 4C, so 4, 5, 6, and 7 all follow the same pattern. You calculate your change in energy, then you calculate your wavelength. And then for part C, they ask you to find the color. And that's where you go to your appendix I. And on appendix I, you see the electromagnetic spectrum. So something that's got a wavelength of 656 puts it over here, which is like reddish orange. So the color for the transition from the third to the second energy level gives you a reddish orange color of light. And then what you were asked to do is to fill in the chart from answers 4 through 7. So Lilly found out that the wavelength was 656 nanometers with an energy of -182, and the color of light was red. And that was due to an electron falling from the third to the second. For number 5, the electron fell from the fourth to the second. And the wavelength of that was 488. And the wavelength, or the energy, was 240, was it 6?
Yeah.
6. And then the electron falling from the fifth to the second, wavelength of 434, -275. Falling from the sixth to the second, you get violet light, 410, and a change in energy of 291. So in other words, it produced red light, violet light, blue light, and green light. Bless you again. So it produced those 4 lines of color. And in the lab, you were looking through the spectroscopes and you were seeing lines of colors for different elements. So hydrogen is right here. You can't see it, but I'll tell you that there is a purple, a blue, a green, and a red. They didn't print it as green, that colored in green. They printed it, they messed that up. But the wavelengths match up. Okay? That's why we still need science people to proofread things, because they had the wrong color there, Kalish. Science person would have caught that right away and said, wait a minute, that shouldn't be blue, it should be green. So what you did in 4 through 7 is going to be the same type of calculations you're going to do in your lab tomorrow. So we're going to get lots and lots of practice of this. Okay. For number 8, could you read number 8 for us? Okay. Mark straight. Ocho.
1 mole of gamma rays, or photons, are traveling with a wavelength of 0.50 nanometers. What is the energy of these waves?
Okay, so I harp on the process of writing down the equations and writing down what you know, because it will help you. Like, learning how to solve a problem is a skill in itself. You can look up what H stands for. You can look up the units on the speed of light, but you can't look up anywhere which equation do I use right now. That's a skill you have to develop. So, we have lots of equations, Jordan. We've got E equals HF. We have E equals HC over lambda. We have lambda frequency equals C. And we have, do we have one more? Oh, yeah. There we go. So, what information are we given? A wavelength. And I'm trying to find the energy. Totally forgot about this thing. Oh, it's on the board. So then, which equation should we use? Which one has wavelength and energy in it? Dana, not Dana, Ava.
The second one.
Second one. So this is the equation that we use. So by writing down what you know and what you're trying to find will help you pick the right equation. Because both these things have to be in it, and that's the only one that it is. So what about Planck's constant? It comes in two versions. One where it's kilojoules per mole, and one where it's joules per one particle. So in the problem there, Brian, are we dealing with one photon or a mole of photons?
One photon?
One, nope,
One mole photon?
one mole of photons.
Okay.
So if it's a mole, there are units. And the speed of light, we know, is 3.00 times 10 to the 8th meters per second. So now we just plug in the numbers. We have to convert the 0.50 nanometers into meters. So 0.50 nanometers, 1 times 10 to the 9th nanometers gives me 1 meter, so that becomes 5.0 times 10 to the negative 10th meters. So that goes on the bottom. And now we can do our canceling. Nope, that doesn't cancel. We need the kilojoules. Seconds cancels with seconds, meters cancels with meters. We're left with kilojoules per mole. When we plug that into the calculator, we get an answer of 2.4 times 10 to the 5th. So the only, in my opinion, the only difficult part here, Brittany, is figuring out which of the 4 equations to use. So any questions on number 8? I feel like I was going a little fast. Oh. You get that, Allison? Now for number 9, they give us a frequency. Could you read number 9, Jenna?
Your microwave emits 1 mole of photons with a frequency of 0.45 times 10 to the 9th inverse seconds. How much energy is produced by this rate?
Okay, so there's my frequency. They asked us to find the energy, Haley. Do we have an equation that's got both E and F in it? First one. So we're going to use that equation. Are we dealing with 1 photon or a mole of photons, Claudia? What does the problem say? Okay, then 1 mole. So that means H will be 3.99 times 10 to the negative 13 kilojoules seconds per mole. And I plug in my numbers. The inverse seconds cancel. I'm left with kilojoules per mole. What's the answer, Ailish?
9.7 times 10 to the negative 4 kilojoules per mole.
So that's the answer, Becky. 9.78 times 10 to the negative 4. Okay? That is not a large amount of energy. It's not that great. So this answer ties into number 10. If the energy for microwaves isn't all that strong, why do we use microwaves to cook our food? Why don't we use ultraviolet light or X-rays or gamma rays? Go a lot faster, right? What blocks gamma rays and X-rays? Lead. So if we use gamma rays and X-rays, we'd cook our food a lot faster. You could get your meal made in 3 seconds, but the gamma rays and the X-rays would leave the microwave and cause cancer. Whereas microwaves are too weak. They can't escape the microwave. Unless you take the microwave apart, Max, but you're never going to do that. So any questions on any of them on the worksheet? Before we dive into the wonderful world of quantum.
Mr. Strauss?
Yep.
What if you like made the microwave out of lead?
Made out of lead. Well, then you could use gamma rays, but the problem with lead is that, lead is, you can get lead poisoning, so you have to make sure that the lead didn't touch your food, and you also have to make sure, like, the outside of it wasn't lead. So, yeah, that's kind of why they didn't do it. Now, interestingly enough, since you did bring that up, the Romans made their drinking cups out of lead. Not too smart. Some people think that's why the Roman Empire fell, because they're all getting lead poisoning and going crazy.
Do you really go crazy when you're lead poisoning?
I don't know. Okay, so take out your packets. We're on page number 8, I believe. Yep, run. If you have colored markers or pens, you might want to use them. You don't have to use them, but you might want to use them. So, the Bohr model. We've had the Dalton model, the billiard ball, the Thomson model, which is plum pudding. We've had the Rutherford model, which is the nuclear model. And now we've got the Bohr model, which is sometimes referred to as the planetary model, where the electrons jump between levels. And the beauty of the Bohr model is that it explains how the spectral lines are produced. So, in the homework, we calculated the 4 spectral lines of hydrogen. Red, green, blue, and purple. And they match up with the spectral lines of hydrogen. Red, green, blue, purple. So that's the beauty of the Bohr model. And when you look through the spectroscopes, you'd see those 4 lines. So the first line was red, the second one was green, third was blue, and the fourth one was purple. And there are actually different thicknesses of those lines. You may not have noticed it because our spectroscopes aren't all that great. But they actually have different thicknesses. Now, if you had a really nice spectroscope, and actually, you might have been able to see this. Some of you, if you looked really closely, you might have been able to tell that some of these lines weren't single lines. They're actually 2, 3, or 4 lines, just really close together. So, Sommerfeld he, with his spectroscope, was able to realize that the green line was not just a green line, it was two green lines. And the blue line was not just one blue line, it was actually three blue lines. And the purple line was not just a purple line, it was actually four purple lines. So you might have been able to see some of those lines being actually 2 or 3 or 4. So when they first realized that these lines were not just single lines, you have to come up with a terminology to talk about it. When they first were discovering quarks, the first pair they named top and bottom, then they named it up and down, and what was the name of the third pair of quarks? Charm and strain, okay? They just named them arbitrary names. So, with these lines, there was a pattern. There's always a very thin line to start it off. They call that line the sharp line, abbreviated S. So the first line in the sequence is always the S line. The second line in the sequence they call the principal line, or P. The third line in the sequence they called diffuse, or D. And the fourth line in the sequence they called fine, or F.
What's the D stand for?
Diffuse, D-I-F-F-U-S-E. So there's always a sharp line. The second one's the principal, the third one's the diffuse, the fourth one's the fine. And you can see a pattern here, right, Melissa? 1 line, 2 lines, 3 lines, 4 lines. Then a scientist by the name of Zeeman put magnets around his spectroscope. And when he did that, something goofy happened. The red line stayed as a single line. Actually, I should say the S line stayed as a single line. The principal line split into 3. So the sharp line stayed as a single line, but the principal line split into 3 lines. It's a total of 4. See, you have a green line. That green line matches up with that green line. That big thick line split into 3. So again, with the next few, the S line stayed as a single line. The P line split into 3, and what happened to the D line? It split into 5. 5 lines. So it went 1, 1, 3, 1, 3, 5. What do you think is going to happen, Kim, to the next sequence? What do you think is going to happen to the 5 line? It's going to break into how many? 7. And that's what happened. So the S line stayed as 1, the P line broke into 3, the D line broke into 5, and the F line broke into 7. So with anything in science, you start with an observation. Okay? Oh, the sun comes up in the east. That's an interesting observation. Now let's make a hypothesis. So they didn't know what was causing this. Their hope was to explain it. The Bohr model could not. And that was a downside with the Bohr model. It couldn't explain what was causing these lines. It could only explain those lines. And the other problem with the Bohr model is that he couldn't explain why they only orbit at certain distances. It would seem to make sense that an electron could orbit at any distance from the nucleus, but it can't. Only at certain distances, quantized distances. So any questions so far?
Mr. Strauss?
Yep.
It says that each of the summerfield lines split in two. Does that just mean they broke apart, not specifically into?
Correct.
Just making sure.
Yes. So a lot of, so the last model of the atom is the quantum mechanical model. And that's what we're going to learn right now, Claudia. This is the correct model, quantum mechanical model. It is not easy to understand. Okay, and honestly, I think it took me 4 attempts before I actually understood it. I learned it in high school once again in freshman college, once again in P-Chem, and then I think it was the second year of teaching that I finally understood the quantum mechanical model. Not the first year, unfortunately, for those guys, but the second year, so I finally understood what is meant. And so to explain the atom, we really have to look at what is the nature of the electron, okay? And don't feel bad, Fletcher, if this stuff seems confusing. It will come to you eventually, but it'll be kind of like coming in out of the fog. It will slowly come into picture, and one day you'll be like, oh, now I get it, okay? So, under classical mechanics, the electron is a particle, right? In your pictures, you always draw it going around the nucleus, like the Earth. You're actually even able to measure the mass of it. Millikan and Thomson measured the mass of the electron to be 9.1 times 10 to the negative 28 grams. It's a really cool experiment. You'll probably duplicate it in college because it's not too hard to separate, set up, I mean. So the electron does have a mass. Therefore, if it has mass, it must be a particle. But a French scientist by the name of Victor de Broglie, was reading what Max Planck was doing and said, well, Planck said a wave, like light, could be like a particle. So light, instead of being a wave, was like little BBs flying through the air, hitting you in the eye. So if light could be a particle, why can't we do the opposite? Why can't a particle be a wave? And so they devised a couple experiments to test this idea that the electron could behave as a wave. And they are called the single slit and the double slit experiment. So you have our observations, now we make an experiment, and then we test our hypothesis. So if the electron is a particle, I've got an electron gun. And if the electron is a particle, the electron would be like bullets coming out of a gun. I'm going to shoot it at a target. but I'm going to put a wall in front of my target. But I'm going to put a hole in my wall. And that is the slit. So, now we make a prediction here, Brittany. If these are bullets, and they're flying, and there's a gap in the wall, will the bullets go through? Yep. And where will they hit the target? Right in the center. They should. Will any of the bullets hit up here? No. Down there? No. So if the electron is a particle, they should go right down the middle and hit the target in the middle. But what if the electron is a wave? So I know this gets to be a little bit weird, but you need to envision the electron as like a water wave or a sound wave coming out of my mouth. So if a wave comes out of the electron gun, the wave will hit the opening, right, and go through. But what happens when the wave gets to the other side? It spreads out again. So where will the wave hit the target? Everywhere. Okay? Where will the wave hit the target with the greatest force or strength? In the center. Okay? And we know this, Ailish, from when we go to the beach, right? You go to the beach, the waves come in, and you're having fun jumping waves. Where's the maximum fun? Right in the middle of the wave, right? Because that's where the wave is the tallest. So if you're going to jump waves, you go for the middle and you're like, yay! Right? Now, if you get a little scared and you think the wave's too big, what do? You go off to the side of the wave. Because the wave gets smaller on the sides. You go, because you don't want you get a little. It's okay to be scared of waves. It's all right. We're pretty big. So, if it's a particle, the bullet should go straight to the center. If it's a wave, it should hit the whole target, but with a greater force in the center. And so they do this experiment. And this is what they found. After 28 electrons hitting the target, this is what it looks like. Where are the electrons hitting? In the middle. What does it look like? Bullet holes. So this would indicate that the electron is a particle. But they kept shooting more of them. That's after 10,000. We're seeing some electrons hitting off to the side, right? After 10,000. After 1,000,000. So what do we see? We see most of the electrons hitting in the center, but some are hitting off to the sides. Plus we see a wave pattern of electrons, no electrons, electrons, no electrons, electrons, no electrons. Wherever it's dark, it means that no electrons hit there. So what we see in the very first picture is a particle pattern. In the very last picture, we see a wave pattern, which made the scientists think that the electron must actually then be both. both a particle and a wave, not one or the other. And then they did a second experiment to test the nature of the electron, the double slit experiment. This one's even more weird. So now there are two openings. If I shoot my electron gun, will any of the electrons make it through? No, they'll hit the wall and be stopped. So there shouldn't be anything on my target. Yep.
What's a wall made of?
It's just, can be made of anything. Usually it's, I don't know, anything. Wood, paper, metal.
So it doesn't really matter at all.
No. What if it's a wave?
Would it break into two waves?
Um,
Because if it's like forced through like two different spots, how does it like?
so let's draw it and see what happens. You shoot a wave. The electron's a wave. What happens when the wave reaches the two holes? It will go through both of them at the same time. So, this led to a very difficult conundrum for these physicists. If the electron is a wave, that means the wave is going to have to go through both openings at the same time,
Wouldn't it split them up?
which means the electron must be going through both openings at the same time. The mass of the electron is measurable. The mass is 9.1 times 10 to the negative 28 grams. How can something with mass go through two openings at the same time? The physical interpretation of that, Haley, would be that the electron is in two places at the same time. So at the quantum mechanical level, which is the subatomic level, it is possible for an object to be in two places at the same time.
So would it split?
It doesn't split.
So they connect together?
What happens on the other side is it forms a interference pattern. The waves begin to overlap.
Yeah, so it would turn, so would it turn into two different waves?
It's two different waves overlapping,
Yeah.
yes. And so you'd end up with an interference pattern on your target. But this is like one of the reasons why it's so hard to kind of wrap our brain around this, is because it's something that's solid, an electron, but it also can be a wave. And so we can't be in two places at once. Or can I? But the electron can. And this is actually what it looks like. So what you end up with is a place where the electrons hit, then no electrons, electrons, no electrons, electrons. So you have this repeating pattern of electrons, no electrons, electrons, no electrons. You end up with an interference pattern. And we're used to seeing stuff like this with waves or sound waves, but not with solid objects like electrons. So now, if you aren't confused yet, then I'm not doing my job well. So what really is the electron? How can it be a particle when it can go through two slits at the same time like a wave?
It's a wavicle.
It's
Well, the answer is, it is both. And what's even crazier is whether or not it's a wave or particle depends on you. When I mean you, I literally mean you. So, and the best analogy I can give you is this.
A bird?
What is that?
It's a duck.
It's a rabbit duck.
So, what do you see, Allison?
It's a duck.
What do you see, Allison? Don't listen to him.
It looks like a bird, but I don't
Okay, you said I don't know. That doesn't help me. What do you see, Max?
It's a duck.
Okay, Max sees a duck. What do you see, Jenna? Carly? A what? A duck.
Bird.
You see a bird. Okay. What do you see, Becky? A duck. What do you see, Mark?
A rabbit.
A rabbit. Okay. So, I'm not sure how you see a bird, but there's a duck
Oh!
and I see a rabbit.
And a
I like the side.
So,
I don't see the rabbit either.
Turn you.
I don't understand.
That's how you
How can a duck, how can a duck be a rabbit? A duck and a rabbit are very different things. A duck cannot be a rabbit.
It's an optical illusion.
So,
But this doesn't
make
help
the bee
because
use
that's
the
like
ears,
natural
it's a
thing.
rabbit.
Oh!
Depends on where you're at. You're like,
I see
everyone
it.
knows that.
Wait, go back. I don't see it.
Look at the
No,
dog,
make
that's an
me
ugly
see
dog.
it.
Here, no, because.
See the
Harry, the
beak?
bill is
The beak is
the ears.
No, honey.
And
there's the bill. There's the eye. That's a duck. If it's like this, there are the ears, there's the mouth.
The ears are
Oh, I
just,
see
they're
it,
not
I see
flopping.
it. Gotcha.
So, who determines whether or not it's a duck or a rabbit?
We do.
You do.
you're like,
The scientist, the observer determines what the outcome looks like. Okay, that's another weird thing about quantum mechanics, okay? The observer, you, determines the outcome. If you want the outcome to be a duck, it's a duck. If you want the outcome to be a bunny, it's a bunny. So, if you go back to the electron, if you want your experiment to show that it's a particle, it will be a particle. If you want the outcome of your experiment to show that it's a wave, it will be a wave. You, as the scientist, affect the outcome, which is not what happens in the real world, okay? If I shoot off a cannonball, I can't sit there and say, you know what? I'd like it to be a wave. It's not going to turn into a wave, okay? You know, it's still going to go and hit.
Do you have any more of those?
Yeah, I do. Mark, and then we'll look at the other ones for
So
fun.
could that mean then that if you had two scientists observing the same experiment, that the experiment could turn out could their results could end up being different?
Yes.
Okay.
And that's what is so mind-boggling. Okay, so boggling. I don't think we bottled minds legally.
I love that one.
I still don't get it.
So what do we got here?
Young woman.
Young woman and old lady.
I don't see old lady. Mr.
Old lady, there's her chin, her mouth. Why are we packing up?
Wait, I don't see the old lady.
Chin, mouth, nose, old lady's eye.
I don't see the young one.
I see the young lady.
Young lady, there's her eyelash, there's her nose, there's her chin, and she's turned away like this.
Which way's the old lady facing? Which way's the old lady facing?
The old lady is like this.
She's looking down.
I really don't see it.
Nose, chin, nose, mouth.
I don't see it. I feel blind. I don't see it.
hey, how's Strauss?
I see it now.
I love that.
A wine glass. A wine glass. And then two people that look like they're about to like kiss each other.
Me and Kim.